Osmosis, this is the movement of water across a membrane, and it's a special case because it only relates to water. So you only talk about osmosis when you're talking about the movement of water. Water, even though it is a polar molecule, it is quite a small molecule. It's polar because of the unequal share of electrons between the oxygen atom and the hydrogen atoms that are attached to it. Because the electrons spend more time orbiting the oxygen, that makes that delta minus, and the hydrogens therefore become delta plus. This allows them to form hydrogen bonds with other water molecules. This leads to the other properties that you know of water, such as a high latent heat of vaporization. So it takes a lot of energy to break these hydrogen bonds and change liquid water into a gas. So that's the high latent heat of vaporization. You've got the fact that all of these water molecules have lots and lots of hydrogen bonds between themselves, and so that's what causes water to have a high heat capacity, which means it's really good at absorbing lots and lots of heat energy. So the temperature doesn't vary very much, even though the environmental temperature may fluctuate quite a lot. The temperature, for example, of the sea doesn't fluctuate, even though the environmental temperature can go from 0 degrees up to 30 degrees centigrade. Okay, osmosis then is the movement of those water molecules across the phospholipid bilayer. Water can move between the phospholipids into a cell, and it moves because there is a water potential gradient. So we don't talk about concentration of water, we talk about a water potential gradient. And what we mean by that is a water potential gradient. If we say that pure water is full of free water molecules, so we have the high water potential is 0 kilopascals, and the lowest water potential is where you have the lowest number of free water molecules. That's usually because it's a very salty or sugary solution, and so we go down into the negative numbers, so we can go minus 10,000 kilopascals because it's very salty, really sugary solution. So water will move from where there's lots of free water molecules and not much salt or sugar, down to where there is lots and lots of salt and sugar and not very many free water molecules. So in this first scenario we have a beaker. In that beaker is a plant cell. If we put that plant cell into pure water, so that's effectively a water potential of 0, the water potential inside will be more negative. That means that water will move into the cell down a water potential gradient. It will move freely through the cellulose layer in the cell wall, and then between the phospholipids in the membrane and into the vacuole, and cause the vacuole to grow. And as it does that, it pushes the cytoplasm onto the cell's wall and makes the cell become turgid. So plant cells in pure water, in a water potential that is higher than the cell contents, will gain water by osmosis and expand and become turgid. In contrast, this cell, if we put that into a really salty, sugary solution, so we give the water potential of minus 1,000, in here it might be, say, minus 300, so therefore water will move down its water potential gradient. That will cause the vacuole to shrink. That will cause then the plasma membrane to come away from the cell wall. So here's our cell wall. So you'll see now there's lots of gaps between the plasma membrane and the cell wall. That's called plasmolyzed. Lyse meaning breaking, plasma to do with the plasma membrane. You could even, if this was a salty solution of NaCl, you might even find that some of that salt has diffused into this space. It can't diffuse through the phospholipid bilayer for what we talked about before, which is that sodium chloride ions are ions, they're charged, they can't cross the phospholipid bilayer, but it can freely go through the cellulose in the cell wall. If we then look at animal cells do not have a cell wall, so what will happen in this case, if we have a lower water potential again than inside the cell will shrivel up, and we call that crenate, because of the loss of water by osmosis. If we put a red blood cell into pure water of water potential 0, it will burst. Because as the water moves in, there's no cell wall to stop the water from moving in to resist the pressure of the water caused by osmosis of water inside the cell. The cell membrane just breaks under that pressure, and we call that hemolysis. and that's osmosis.